So we have a few examples that we're going to walk through. All right, so I like to start with the don and the dod. So we have 4x squared on top over 3x squared minus 18x plus 27. So first, let's do our horizontal asymptote business. To do that, I'm just going to write down a note to myself, the don and the dod, and the degree of the numerator is 2. The degree of the denominator is 2. Notice I am not looking at the 4 or the 3. I'm not looking at anything else. I'm only looking at the don and the dod. So looking at my degree of the numerator and denominator, it is equal powers because they are the same. And our notes tell us that if they're equal powers, we look at the leading coefficients. So now let's look at the leading coefficients, and it's 4 over 3, so that's my horizontal asymptote, 4/3. Now, I just misspoke. I just said 4/3. It should be y equals 4/3. These asymptotes are equations. Often they are lines, they could be other curves, but they are equations, so make sure you write them as such. Y equals 4/3. All right. Now, let's move on to the vertical asymptotes and wholes, because that requires a little bit more work usually. So let's deal just to the side, like to find my domain. So I do this, I just write domain work. So I'm going to set my denominator to be not equal to 0. So here's this. I see, oh, well, there's a 3 in everything. So I'm going to pull out a GCF of 3. And then I'm going to actually then divide everything by 3 because I don't need it. 0 divided by 3 is 0. And then I can factor. This is a perfect squared trinomial, or what multiplies to be 9, adds to be -6. We can factor directly to that and get x minus 3 squared. So there's x minus 3 times x minus 3. Set each equal to 0, and we get that x is not allowed to equal 3. All right, so our domain is that x cannot be 3. So I have this one value, and I need to decide, where does it go? Is it a vertical asymptote or is it a whole? Well, to do that, let's see if anything reduces. So here I have it written down, our g of x function written down where it's fully factored. Does anything reduce? Nope, I cannot reduce anything. So we have no wholes. So I have air quote holes. Its fancy name is removable point of discontinuity, but we have no wholes. So then that means that this factor, x minus 3, is then our vertical asymptote at x equals 3. Notice, our domain restriction was that x cannot equal 3. But our vertical asymptote is on that location, is on that x equals 3. X can't equal 3 because we have a vertical asymptote there at x equals 3. So vertical asymptote at x equals 3. All right, so that's really it for the new things for this particular function. X-intercepts, Y-intercepts, we've been doing this for a long time, but let's do it anyway. So for my X-intercept, I'm going to set the numerator to be equal to 0. 4x squared equals 0. So for x, well, x equals 0. So since x equals 0, then I can, I instantly then know that if I have an X-intercept at 0, that means that's 0, 0. So that means that is also the Y-intercept. But I could check it. So plug in 0, and I end up with 0 over 27, which is 0. Remember, 0 over something, that's okay. Something over 0, that's a no-no and undefined. So this right here that's okay. That's just 0. Remember, we can have multiple X-intercepts. I can have only one Y-intercept. So once I knew that I have an X-intercept at 0, 0, I knew that my Y-intercept was at 0, 0. All right, so your task for this lecture is not to worry about any points or anything other than what you've done right here. I just want you to put this information on the graph. And next lecture, we'll literally just pick a few dots and connect the dots. But today, let's just put our information on the graph. So in terms of points, I really only have this one point at 0, 0, and we have our vertical asymptote at x equals 3, horizontal one at y equals 4/3. So here's my horizontal asymptote at y equals 4/3. And here's my vertical asymptote at x equals 3. And then we have our x and y-intercept right here. All right, here's just a little technical note right here. It says that what if I would have had x minus 3 over x minus 3 squared? What then it's just a little technical note, and some people go back and forth about this, but you can think of it as that there's a hole and a vertical asymptote on the same location, but graphically the vertical asymptote wins, because if I just have a hole, then cool, but the vertical asymptote is actually affecting all the points around it. We'll see something like this in the next lecture. But you can sort of kind of argue both, but you want to be able to have a specific location for the hole because you want to be able to evaluate it. But yeah, give or take. Okay, let's look at this next example. So first, let's determine, we have this square on top and a cubic on bottom. So because of that, we can determine our horizontal asymptote quickly by figuring out the don and the dod. So the degree of the numerator is 2, degree of the denominator is 3. That is bottom heavy. Bottom heavy, they are easy. They have a nice big bottom, super easy. So anytime it's bottom heavy, it is y equals 0 every time. So y equals 0. Make sure you say y equals and not just 0. Cool. Next, let's do our domain. Because from our domain, we then sort our values from our domain and produce our vertical asymptotes and holes. So let's take a look at this. I have x cubed plus 6x squared plus 5x minus 12. That's my denominator. We got to factor it. All right. So I'm going to check and see if I can factor by grouping. When I do, I can pull out an x squared. I'm left with x plus 6. And then over here, we notice that there's nothing in common. So I don't end up with an x plus 6, so I cannot factor by grouping. So then that means we have to move on to what we saw in the last lecture, which is the possible rational root theorem. So possible rational root, my constant is 12. So the factors of 12 are 1 and 12, 2 and 6, 3 and 4. And it could be plus or positive or negative. We have a 1 for the leading coefficients, or just over 1. So we have these 6 possibilities. I know because, just pretend I did it already, I grabbed negative 3 first, and do my synthetic division. Dropped out a 1, multiply, add, multiply, add, multiply, add. We end up with 0, and it works. So that means I could factor out an x plus 3, because this is the root. The factor is x plus 3. Notice the sign difference. So I factor out the x plus 3, and I'm left with a 1, x squared plus 3x minus 4. And then so we can factor this. What multiplies to be negative 4 and adds to be a positive 3. Well, that's a positive 4 and a negative 1. And so my domain restrictions are that x is not allowed to be a negative 4, a negative 3, or a 1. Now, without me looking at any other parts of this function, all 3 of these could be holes. All right? All 3 of them could be vertical asymptotes. We could have a vertical asymptote and 2 holes, or 2 holes and a vertical asymptote. All right? So basically imagine you have 3 things, and your next task is just to sort them into being a vertical asymptote or a hole. So to do that, I need to see if anything reduces to 1. So I already have my denominator factored, hot dog. All right, now I need to just factor my numerator. So what multiplies to be 12 and adds to be 7? That's 3 and 4. So here's h of x factored. And notice x plus 4 over x plus 4 reduces to 1. X plus 3 over x plus 3 reduces to 1. And I'm left with just h of x is 1 over x minus 1. So remember our notes. We said that for vertical asymptotes and holes, step 1 is we find our domain restrictions, right? That's step 1. Did it. Then we are going to be sorting them. If something reduces, it's a hole. Well, I just had 2 things reduce, so those 2 factors are going to lead to my holes. And then what's remaining in the denominator, what's remaining are vertical asymptotes. All right, so here we are. So that means that these factors lead to holes, and then this factor that's left over, this x minus 1, is a vertical asymptote. So I have a vertical asymptote at x equals 1. So now I need to find the y values of these holes. So for my hole at negative 4, now I know it's negative 4 because I take my x plus 4 and I set it equal to 0, or I know that this x plus 4 leads to that negative 4. So So then plug this -4 into x, and I get 1 over -5, or a -1/5, so I have a hole at -4, comma -1/5. Then take the -3, plug it in, and I end up with a -1/4, so I have a hole at -3, -1/4. All right, now let's talk about x and y-intercept. So for x-intercepts, we set our numerator to be equal to 0. It's important for you to set the reduced one equal to 0. One is just easier work, but look at what is unnecessary. If you set this equal to 0, you'd be setting x plus 4, x plus 3 equal to 0, and you'd get some values that, in theory, would be your x-intercepts, but they're not your x-intercepts because they've gotten reduced out of the function. So because of that, it's best just to set your reduced numerator equal to 0. So I do, and I get 1 equals 0. Wait, what? 1 equals 0? That is not a true statement. That is a false statement. So because that's false, that means we have no x-intercept, which should make sense. If I asked you to graph 1 over x minus 1, you should be pros at that by now. We spent a whole chunk of lectures talking about transformations of functions, and this is just the parent function, the 1 over x parent function, shifted to the right 1 unit. And so we still have our horizontal asymptote at x equals 0, which is here, so then the graph isn't crossing. Now, just to note, we'll see this, I think, in just a second, but you can cross the horizontal asymptote. That is a possibility. We will never cross vertical asymptotes, but horizontal asymptotes are possible to cross. So just because you see a horizontal asymptote of y equals 0 does not mean that that there is no x-intercept. All right, last thing, for our y-intercept, plug in a 0 into the function, and I get 1 over -1, which ends up being a -1, so the y-intercept at 0, -1. So let's put all of this information onto our graph. We have our horizontal asymptote, we have our vertical asymptote, we have these two holes, we don't have an x-intercept, but we do have a y-intercept. So we put all this together. So here's my horizontal asymptote at y equals 0. Vertical asymptote at y equals 1. I'm sorry. Let me try all that again. We have our horizontal asymptote at y equals 0. Our vertical asymptote at x equals 1. I had my x's and y's confused for a second there. Then we have these 3 points. My y-intercept, which I did not label, shame on me. So we have our y-intercept at 0, -1. And then we have our hole at, we have 2 holes. We have one at -3, -1/4, and the other hole at -4, -1/5. All right. So in today's lecture, that's it. That's all we're doing. In a future lecture, I will then be connecting these dots and figuring out where a few dots are over in the on this side of the vertical asymptote. All right. Another one. K of x is -x over x squared minus 9. All right. So we have it is bottom heavy because it is the degree of the denominator is 2, degree of the numerator is 1. Bottom heavy, automatically y equals 0. All right. Next, now we need to deal with the domain, vertical asymptotes, and holes. To do that, I'm going to grab my denominator, set it to be not equal to 0. So let's do this. 2 ways to work this one. You can set it to be not equal to 0, add the 9, square root both sides, and you end up with plus or minus 3. Or you can recognize that this is the difference of 2 squares, and we get x plus 3x minus 3. And then you set each factor to be equal to 0, and then solve, and so you get x is -3. X can't be -3, and x can't be 3, so x can't be plus or minus 3. Don't care which way you do it, you end up with the same thing. X cannot be positive or -3. So, just to be clear, I've then combined this information into a factored form of k of x, and I noticed that nothing reduces. Since nothing reduces, we have no holes. So we have no holes, so that means that both of these domain restrictions are our vertical asymptotes. All right. Next, x-intercept. So notice what I said a second ago, just because you see y equals 0 does not mean we automatically have no x-intercepts, because we do. So take our negative x and set it equal to 0, multiply both sides by -1, x is 0. So we have an x-intercept at 0, 0. which automatically means we have a y-intercept at 0, 0, but let's just check nonetheless. So we plug in a 0, 0 over 0 squared minus 9, 0 over negative 9 is still 0. That's okay, that's fine. Again, 0 over something is okay. That's 0. Many students try to tell me that there is no y-intercept, that it's undefined. No. Sorry, that's okay. This is okay. It's wrong to say that something over a number, 0 over a number is undefined. All right, then put all this information together. We have a vertical asymptote at x equals negative 3 and x equals positive 3. We have a horizontal asymptote at y equals 0. And we have both x and y-intercept at 0, 0. So now notice, and that's what this note is saying, our function is going to be able to cross over. So it might touch and turn. It might cross through like this. It might cross through like that. There's lots of different sort of kind of ways that they can do this, but it's okay while you're near or around the origin that we might cross the horizontal asymptote. I've even seen functions, not this one obviously, but they'll do this, it'll cross, and then sort of kind of come back like that. That's because with the horizontal asymptote is the end behavior. As x approaches positive infinity or x approaches negative infinity, this is what's happening. Not so much around these numbers, but infinity is when these weird things happen. Just to note, these vertical asymptotes will never be crossed. All right, if it can't equal negative 3 here, it can't equal it up here or here or here. All right, so these vertical asymptotes are impenetrable walls. The horizontal asymptotes are just guides. All right, so that's it. It's just about recognizing these things and just prepping our graphs. In a later lecture, in our next lecture, we're going to then literally just pick a few key points and graph them, and then do domain and range things. All right. Hope this helps for you to do your homework, and I will see you next time.